Hello, and welcome to our project video. We are Team 24021, and today we'll be telling you about NumaBrace, a wearable electronic carpal tunnel relief brace. Before we start, we'd like to take a second to introduce you to our team members.
I'm Wakil Rahman. I'm a biomedical engineering major and the team lead for this project.
I'm Michael Cesar Torres. I am an electrical engineer and I am the electrical lead for this project.
My name is Aiden Soche. I am a biomedical engineer and I'm the team's procurement lead.
My name is Christian Vanasco. I'm a mechanical engineering major and I'm the team's mechanical lead.
I'm Zach Amstutz. I'm a biomedical engineer and I'm the biological systems lead for the team.
My name is Noah Faluteri. I am an electrical engineer. I am the software lead.
Carpal tunnel syndrome is the most common form of compression neuropathy and affects more than 10 million people in the United States alone.
For those with carpal tunnel, the median nerve is compressed by the transverse carpal ligament, causing pain, numbness, or weakness in the hand, often impacting thumb and finger movement and making daily tasks challenging. Treatment methods for carpal tunnel syndrome are invasive, with carpal tunnel release surgery being the most effective. Yet, this operation comes at a high cost, involves a prolonged recovery phase, and may result in diminished hand strength post-treatment. Our sponsor, Dr. Zongming Li, is an expert in the field of carpal tunnel research and hand mechanics and has over 25 years of experience working in the field. He has patented a non-invasive treatment method, radial ulnar wrist compression therapy, which has shown results comparable to surgical interventions without the associated risks and downsides.
This novel therapy consists of application of pressure to the hamate bone of the hand, which is right here. This increases space in the carpal arch in a mechanism similar to that of squeezing a business card like this, relieving pressure on the median nerve and providing with pain relief.
Our device, NumaBrace, is a 3D printed multi-material brace that combines pneumatics and electronics onto a single rechargeable system to provide radial ulnar wrist compression therapy. A rubber bladder sits inside the brace to cyclically inflate and deflate, while a force sensor allows the device to regulate the amount of force placed on the user's hand. In contrast to the manual device used in Dr. Lee's research, NumaBrace offers an automated therapeutic experience designed to seamlessly fit into a user's life without disruption. The design process for NumaBrace consisted of extensive requirements analysis and rapid prototyping. With each prototype, our device grew closer and closer to our vision of providing an effective and non-invasive solution to manage carpal tunnel syndrome. We demonstrated the performance of our device through testing, demonstration, inspection, and analysis. NumaBrace not only met our initial design requirements, but exceeded them, resulting in a device that is ready to redefine carpal tunnel syndrome treatment.
The system architecture has 4 sub-assemblies. The 4 sub-assemblies are hand brace, pneumatic, electronics, and battery. Using those components, we devised a system block diagram which displays the internal inputs and outputs to the system. The block diagram shows how components are interfacing with each other. At the start of our project, we established a number of functional requirements. These were used to create our system requirements, which has 5 main categories, namely performance, user comfort, power, interfacing, and safety.
Design of the brace began in the U of A College of Medicine Sensor Lab. Using a device called the EinScan Pro, a handheld 3D scanner, the team was able to create a 3D model of my hand and forearm in a resting position. This model was then imported to Mediace 3D, an industry-standard software primarily used for the creation of bespoke orthopedic braces. Using Mediace, the team was able to create a brace that not only fully covers the hamate region, but also properly restrains the thumb. The brace model was then moved to SolidWorks for further modifications. Using SolidWorks, the team was able to create a housing for the electronic and pneumatic subassemblies, as well as slots for adding Velcro straps. Additionally, SolidWorks was used to split the model into 2 interlocking parts. The larger part was 3D printed out of rigid PLA, while the smaller part was made of flexible TPU. This composite construction simultaneously provides proper bracing of the thumb, as well as allowing enough flexibility and bending for proper tightening and fit, thereby preventing force loss through looseness. This brace design also fulfills our design requirements for size and weight, as it is less than our maximum constraint values of 2.5 pounds and 3x3x2 inch housing space.
The pneumatic subassembly's main feature is to ensure we reach the desired pressure of 10 to 20 newtons of force on the treatment area in a cyclical manner. This is done using 5 components: the air pump, solenoid valve, force-sensitive resistor, the electronic subassembly, and a rubber bladder used for inflating. The process starts with an air pump pushing air into the solenoid valve, which is then used to control the amount of airflow into the bladder. The valve will close when the desired pressure is reached, and it will remain closed for 5 minutes, ensuring no air escapes. After this, the valve will open to release the air, turning off the treatment. This process will repeat itself every 5 minutes. The FSR is used to ensure that the force does not go over 20 newtons. If the force exceeds 20 newtons, the valve will open in order to allow the user to restart the treatment. When assembling the pneumatics, we first had to verify that the FSR would be able to give accurate readings. To do this, we converted the resistance readings received from the FSR into a force reading in newtons. This allowed us to calibrate the FSR and use it for safety testing. This calibration was then tested using a weight plate to ensure accurate readings and was found to have an accuracy within 10%.
The electronics and battery subassemblies are integrated onto a single printed circuit board to produce a compact and cohesive system. The electronic subassembly interacts with the pneumatics to regulate radio-ulnar wrist compression therapy. The GPIO pins on the microcontroller are limited to a low current output, which is why MOSFETs are utilized as low-side switches to deliver the necessary power to the pneumatics. The battery subassembly is equipped with a charge controller, a boost converter, and overcharge protection circuit, ensuring safe charging and discharging of the lithium polymer battery. Significant time and effort were spent in assembling and testing the PCBs to determine feasibility and demonstrate functionality. Altogether, these subassemblies address the requirements for power, interfacing, and safety.
Our budget was set at $4,000 to purchase necessary components and create the device our sponsor was requesting. We used approximately half of the budget and have broken down our spending by phases of the project. As we can see, most of our spending went toward creating the final iteration of the project. This was mostly due to multiple attempts at decreasing the space needed to house the electronics. Resources and effort we have put into this project, we were able to deliver our sponsor a fully functioning prototype alongside a technical data package with turnover assistance, this video, and a poster. Moving forward, our sponsor plans to use our development of an electronically driven compression method to explore other design options regarding the location of the system components. With the goal in mind to create a slim, comfortable design, our sponsor intends to build off the work we have done to take this device into clinical trials in preparation for market production. The current stage in the development of this product makes a technology readiness level of 7 a realistic evaluation. This is because the technology associated with the final product has now been developed, and all that's left is to make adjustments to fine-tune some of the assembly. By completing our project, we have provided our sponsor one design of a device that uses an electronically driven system to administer radio-ulnar wrist compression therapy. We would like to thank our sponsor, Dr. Zhongming Lee, his lab manager, Trevor Green, and our mentor, Pat Caldwell, for their continued support throughout the year. For more information, contact Dr. Lee at leezongming@arizona.edu.